Hi, this is our 4510 final project video by James Still and Adrian Chung. Our topic is Gödel's completeness theorem, which is not to be confused with Gödel's incompleteness theorem. And yeah, see ya. To start with, we will begin with a discussion of structures. We've already been interacting with, using, and constructing structures throughout this course plenty, but let's formalize its definition a little bit. Generally speaking, a structure has three components: a base set, which denotes the domain or universe of our structure, a set of operations or functions on our base set, and a set of relations on our base set. For example, we can define a structure Z which has a base set consisting of the set of all integers, which allows for addition, multiplication, and the additive inverse or negation, and has constant identity relations for integers 0 and 1. This defines a structure which essentially allows for performing operations on the set of all integers to produce all other integers. We can construct similar structures for other fields, such as the set of all rationals, irrationals, reals, and so on. Some other examples of structures include graphs, DFAs, NFAs, PDAs, which we covered in this course, and databases, especially relational databases. Next, we need to define what a signature is. A signature is usually denoted by a lowercase tau symbol. This is simply a set of function symbols, typically denoted f1, f2, f3, and so on, and relation symbols denoted by r1, r2, r3, and so on. Each symbol is auto-equipped with an arity, which is simply the number of operands, or as we like to say in computer science, the number of arguments which each function or relation takes as input. For example, the signature of a basic graph may contain a single function called e, which determines whether two arbitrary nodes are connected via an edge. This function would have an area of 2 since it takes two nodes as input and outputs a Boolean value. The signature of a structure Z, which we defined earlier, would consist of the addition, multiplication, additive inverse operators, as well as the constant identity relations for 0 and 1. The arity of our addition and multiplication operators would be 2, while the arity of our negation operator would be 1. The arity of our 0 and 1 identity relations would be 0, since they're both constant. We now define a tau structure. This is simply a structure with a base set B whose functions and relations come from a signature tau. In other words, a tau structure is just a structure with a signature. Given a base set with B with signature tau, we denote its tau structure as underlined B. Next, we are going to discuss redux and expansions of structures. The main idea is that for both of these, the domain or base set of a structure will remain the same, but its signature tau will change. Given a tau structure B, consider a signature rho, which is a subset of tau. We can construct a reduct of B, which we'll call structure A, using rho. Keep in mind, A and B share the same base set, or domain, but the signature of A is a subset of the signature of B. Thus, structure A would be a reduct of structure B. And on the flip side, structure B would be an expansion of structure A. For example, we can construct a reduct of the structure Z, which we defined earlier, by defining a tau structure whose base set is a set of all integers, but whose signature only contains the addition operator. Similarly, structure Z would be an expansion of this structure. That pretty much wraps up structures. Next, we'll be defining various terminologies of first-order logic. First, we'll define tau terms, which are essentially the words or sentences processed by tau structures. Tau terms are defined inductively by continuously adding three components. These components are constants, variables, and functions. For example, polynomials over real numbers are tau terms over the signature that contains addition and multiplication, as well as real constants for the coefficients of the polynomial. Here, constant symbols in tau terms include any arbitrary constant, 0, 1, 2, pi, e, the gravitational constant g, and so on. Variables such as x and y are also contained in tau terms. We usually use x, y, z, etc. for polynomials, but they can really be any arbitrary letter or symbol. Last are functions. These are any combination of functions from tau terms applied to tau terms. All real polynomials are just combinations of addition and multiplication applied to real coefficients and variables. Now we can talk a bit about the semantics of tau terms. Given an arbitrary tau structure A and tau term t, we can let t parentheses x1 to xn close parentheses denote that all variables in t are from x1 to xn. Note that this is a subset, not an equality. Since we have some string of x1 up to xn, tau term t describes an operation over tau structure A with arity n. In other words, we can see t as a function or operation evaluated over tau structure A with n arguments, which we denote T superscript A. We now define tau formulas. Conceptually, if tau terms are akin to words, then tau formulas are akin to sentences. Like tau terms, tau formulas are defined inductively. We can define all tau terms inductively from three basic tau formulas, which we call the atomic tau formulas. First is simply T, or true. This is pretty straightforward. Next is T1 equals T2, where T1 and T2 are arbitrary tau terms. Lastly, we have R open parentheses, T underscore 1 to T underscore K, close parentheses, where R is a relation symbol from our signature tau with arity K. Together with these three cases comprise our atomic formulas. From any tau formula, we can define another tau formula using any application of logical operators or quantifiers. Thus, we can define any tau formula inductively from our atomic tau formulas. So for a tau structure A and tau formula phi, we let phi parentheses x1 to xn close parentheses denote that all free variables in phi are from x1 to xn, and we let phi superscript A subset equals A superscript n denote all satisfying assignments of x1 to xn of phi such that phi is true. By the way, a variable is considered free if it is not bound by some quantifier. For example, if we have a tau formula phi just be a tautology, then phi superscript A would be equivalent to the set containing every possible assignment of the variables x1 to xn. We say A satisfies or models phi of a1 up to a of n if the variables of a1 up to a of n are in phi superscript A. Lastly, we define a tau sentence as a tau formula without free variables. For an arbitrary tau structure A and tau sentence phi, A will always satisfy phi, or A will never satisfy phi, which is the same as saying A satisfies not phi. We now define tau theories. Tau theories are defined as a set of tau sentences. For a tau theory T and tau structure A satisfies T if and only if A satisfies phi for all phi in T. This is equivalent to saying that A is a model of T. We note the following, that T is satisfiable if it has a model. T satisfies phi if every model of T satisfies phi. T is called complete if T is satisfiable and either T implies phi or T implies not phi for every tau sentence phi. Note that tau theories can be infinite. In contrast, tau terms and tau sentences are finite. Okay, that was a lot of definitions, but we can finally now look at the completeness theorem. For a theory T and sentence phi, T proves phi if and only if phi is true in every model of T. This intuitively makes sense since anything that is true in a model should be provably true from within that model. The forward direction is denoted by the soundness theorem, and we will not cover that in detail in this video. The reverse direction is Gödel's completeness theorem, and we will be covering its proof in detail. But first, we need to define what makes something provable in the first place. Okay, so formally, what is a proof? That might be a bit confusing since this video is literally on a proof of Gödel's completeness theorem, but bear with me. Let's define a proof using the terminology we've given you thus far. For a theory T with sentences phi subscript I, a proof in T consists of a finite series of sentences phi 0, phi 1, phi 2, up to phi n, with lexicographically earlier sentences having implications on later sentences. Remember modus ponens. If T implies for all x phi, and T implies for all x phi implies psi, then T implies for all x psi. So if phi 0 and phi 1 are sentences in our proof which behave like the assumptions necessary for modus ponens, then phi 2 may be a sentence acting like the conclusion of a modus ponens of phi 0 and phi 1. For all implications or chains of implications, they must start with logical axioms. In our example, this would be phi 0 and phi 1. We denote T vertical line dash phi as T proves phi. This is only the case if there's a formal proof in T that ends in phi. Let's revisit what we detailed earlier. Given a theory T and sentence phi, phi is provable from T if and only if phi is true in every model of T. The forward direction is the soundness theorem. This is proven by inducting over the length of the formal proof. The reverse direction is Gödel's completeness theorem, and it's a bit trickier. Formally, we will now go through its proof. Given the formalization of proofs which we just defined, we will begin by specifying the logical axioms which we will then use in our proof of the completeness theorem. We will only define 10 axioms for the sake of our proof, but keep in mind that this is an arbitrary choice and the number of axioms for a proof system can be any number, even infinite. First, we have our logical axioms for equations. For all variables x, y, and z, we define the following. We define our reflexivity axiom, x equals x. We denote this as E1. We define our symmetry axiom, x equals y implies y equals x. We denote this as E2. We define our transitivity axiom, parentheses x equals y and y equals z close parentheses, implies x equals z. We denote this as E3. For the next two axioms, we define f and r as a function and relation respectively in our signature tau, both with an arity n. We define our functional congruence axiom. For all x1 to xn, y1 to yn, x1 equals y1 up to xn equals yn implies f of x1 to xn equals f of y1 to yn. We denote this as E4. Lastly, we define our relational congruence axiom in the same manner as E4, but using r instead of f. We denote this as E5. We now define our logical axioms for quantifiers. For every tau formula phi with free variable y and variable x, we have that for all y phi implies for all y, and for all x phi. We denote this as Q1. Clearly this holds for all tau structures. X is a dummy variable with no effect on the truth value of this sentence. For every tau formula phi with free variable y and free variable x, the axiom says that for all y, if for all x not phi, then there's no x such that phi. We denote this as Q2. It's clear that Q2 also holds for all tau structures. For every tau formula phi with free variables y and x, and a tau term t with variables y, the sentence for all y phi replace x by t implies there exists an x, phi. We denote this as Q3. Where y bracket x arrow t close bracket is y with x replaced by t. Again, it is clear this sentence holds for all tau structures simply because the term evaluated for some values in the structure provides a witness for the existentially quantified variable x. For all tau formulas phi with free variables y and psi with free variables y and variables x not free in phi, we have the axiom for all y, for all x, phi implies psi if and only if psi implies for all x, psi. We denote this axiom as Q4. We now proceed with our final axiom about tautologies. We define phi as a propositional tautology with variables x1 to xm using capitalized x's, and we denote psi as tau formulas with free variables x1 to xn with undercased x's. Then for all x1 to xn, phi of psi 1 up to psi m is valid. We denote this as taut. This formula is obtained by replacing xi by si. Again, it is clear that since phi is a propositional tautology, that taut is valid. We will now begin with the main part of Gödel's completeness theorem proof. We are trying to prove that given a theory T and a sentence phi being true in every model of T implies that T proves phi. We proceed by proving the contrapositive. T does not prove phi implies that phi is not true in every model of T. This is equivalent to saying that some model of T satisfies not phi, or that the union of T and not phi has a model. Thus, if we can construct a model of T that satisfies not phi, we have proven the completeness theorem. We'll do so by using a technique called Henkin construction. The idea is to add new constant symbols not in the signature of T and phi, the signature which we started with. Let's outline our Henkin construction. First, we'll define a Henkin theory as a tau union rho theory such that for every tau union rho formula, phi of x, there exists a constant c called the Henkin constant in the signature rho such that the theory T contains the sentence, if there exists an x such that phi of x, then phi of c. To perform a Henkin construction, we can either take an existing consistent theory and add the quantifier, there exists an x such that phi of x implies phi of c, where c is a Henkin constant, or we can take an existing theory with only constants. We will perform a similar construction in our proof. We will be using something called finite completeness, which is a stronger version of consistency. A theory T is finitely complete if and only if either T proves phi or T disproves phi, but not both. This is a combination of consistency and syntactic completeness, which you may have seen before. The proof of the completeness theorem relies on two major lemmas. The first lemma says that every finitely complete Henkin theory T has a model A constructed from Henkin constants. The idea is that we can construct a model A by reading the constants off the theory. Recall that A is a model of T if and only if A satisfies all sentences in T. So we need to prove that for every sentence phi in T, A satisfies phi if and only if T proves phi. We do this by inducting over all phi in T. Here is a sketch of a proof for lemma 1 by induction. Our base case is the atomic formulas or equalities, relations, and formulas such that phi is an atomic tau formula. Since we can construct any other formula by negation, conjunction, and existential quantification, we show the statement holds true for those cases in our inductive step. This can be done with a combination of first-order logic definitions and our logical axioms. Thus, we have proven every finitely complete Henkin theory T has a model A. Our second lemma states that if phi has no proof in T, then T union not phi can be extended to a finitely complete Henkin theory T star. Note that if phi has no proof in T, then T union not phi is consistent. Recall that to construct a Henkin theory, we can take a consistent theory and add the necessary existential statements. Formally, we define our Henkin constants, rho, as the union of an increasing sequence starting with rho 0 as the empty set. For every tau union rho I, formula phi x, we add a new constant c phi. Every row I in the sequence extends the previous row by the current c phi. Rho is then defined as the union of all rho I. Then we define theory T I as the extension of the previous T by all sentences of the form there exists an x where theta of x implies theta of c of theta. For all tau union rho I, formulas theta. Note, by the way, the second to last line should really say theta to avoid reusing our phi variable. Since we're extending from t union not phi, that is our t0. We'll now continue with the rest of the proof. We now proceed with our proof sketch of lemma 2, where we need to prove that one of these extensions is finitely complete. First, we must show that all ti are consistent. Thus, the union of all ti is also consistent. We do this by taking the set of consistent tau union rho theories that contain the union of all Ti and partially order the set by inclusion. By Zorn's lemma, there must be some maximal element, we call this T star, and this is our maximal constant tau union rho theory containing the union of all Ti. By maximality, we can show that not phi is in T star for any tau union rho sentence phi. Thus, T star is finitely complete. Now that we've proven both of our lemmas, we can easily prove the completeness theorem. Recall that we are trying to prove the contrapositive. If phi is not provable in T, then phi is not true in every model of T. We begin by extending T union not phi to a finitely complete Henkin theory T star. This uses lemma 1. By lemma 2, we know T star has a model. Thus, the reduct to the original T union not phi also has a model. This means that phi is not true in every model of T, and we have proven the completeness theorem. This completes our proof. Oh my god, we finished. Thank god. Okay, implications. An immediate result of the Gödel's completeness theorem is that the only way a theory can be incomplete is if there is a model in which some statement is true and another where that statement is false. For example, the statement there exists a number n where n times n equals 2 is true in reals but false in rationals. This makes intuitive sense, right? It's important to note, however, that Gödel's completeness theorem only proves completeness for first-order logic. There's no completeness theorem for higher-order logic, so we can't say all of math is complete. Soundness, however, is a fundamental property in all logics because we need to make sure that the conclusion really does follow from the premises in the proof. This theorem also implies the compactness theorem of first-order logic, which states that a theory is satisfiable if and only if all of its subsets are satisfiable. This theorem has many applications in mathematics. Finally, we would like to mention Gödel's incompleteness theorem, which we covered in this course. Yay! At first glance, it might seem that the completeness theorem contradicts this, but the definition of completeness is a bit different here. Earlier, we mentioned syntactic completeness, which is what the incompleteness theorems use. Here, completeness or semantic completeness refers to the converse of soundness. The completeness theorem says that anything true in all models is provable. The incompleteness theorem, however, says that there is a statement that is true in a specific model that is not provable. So these theorems do not contradict each other. And that pretty much wraps up everything we wanted to say about Gödel's completeness theorem. Thank you for listening and watching. Goodbye.